Welcome back to the channel. Now let us talk about Bernoulli's equation. What I want to do is explain the concept of Bernoulli's equation, how to derive it, and make sense of it to you, okay? That is what I want to do in this video. We are not going to be solving questions. In the next video, I'm going to now take fluid mechanics altogether and we'll solve questions, even including using Bernoulli's equation. But I might not be able to derive again there, so that's why I want to derive it in this video. Now, Bernoulli's equation. First, you have to know the Bernoulli's law, okay? And that law states that the pressure energy for a fluid, let me write this way, it states that for a fluid, an ideal fluid actually, for an ideal fluid in steady flow, for an ideal fluid in steady flow, comma, the sum of the pressure energy, kinetic energy, and potential energy per unit volume of the tube is constant for a streamline flow. Is constant for a streamline flow. So there are some conditions to take note of here. First, the fluid has to have a streamline flow and not a turbulent flow. So meaning that this law does not apply for a fluid in turbulent flow. Okay? Then of course another thing is that it is also applicable we are talking about an ideal fluid. Okay, let me make sense of this equation, of this expression. The overall equation is written like this: that P1 plus half rho V squared plus rho GH is equal to a constant C. Alright, so that's what the rule is saying. Now I want to make sense of all of this. Now, how did they get pressure here? Okay, pressure energy, okay? That is basically pressure energy, that is basically pressure per unit volume. Okay, that's what resulted in this guy. Pressure energy simply means work done per unit volume. That's the meaning of pressure energy. Okay, let me make sense of that. So remember that if a fluid, and I'm going to, so this is where I want to derive now, the derivation now. The derivation of proof, okay, is basically the proof that it makes sense and it is correct and true. Alright, so now let's consider a fluid that is flowing from point 1 to point 2 in a tube. So this is going to be our tube, alright, this is going to be our tube, and a fluid is flowing within it from point 1 to point 2. Alright, now it's going upward, keep that in mind. So a fluid is flowing from point 1 to point 2. Now the pressure in the fluid is going to be the force per unit area, isn't it? So the force on each fluid is going to be pressure times area. Does this make sense? Good. Now keep in mind that the pressure that the fluid is going to impact on the walls of the container is going to decrease with the speed. If the speed of the fluid is high, the pressure will be low. Okay, those are the things that you have to know about this part of the derivation first. Okay, if the fluid is moving really fast, the pressure will be low. Why? The reason is because it is having to flow very quickly, so it doesn't have enough time. The fluid does not have enough time, and it's in laminar flow. So because it's in laminar flow, it cannot really interact so much with the walls of the container. Hence, the pressure at any point on the tube is going to be less for a high velocity moving fluid. But for a low velocity moving fluid or a slow moving fluid, the pressure at every point is going to be high. Why? Because the fluid is flowing sluggishly, and for that reason, it is having time to interact with the wall of the container, to collide with it. Is that clear? It's spending more time on the wall of the container than a fluid that is flowing speedily. Do you understand? Each packet of water or each packet of the fluid, each volume of the fluid is spending a lot of time interacting with the wall of the container than. Do you understand now? So that's why as velocity increases, the pressure decreases. Okay. Now what was I getting to? Now what we want to talk about in pressure energy is the work done, right? Now work done per volume. Now what is work done by the fluid? Work done by the fluid is given by the force on the fluid times the distance it moves, right? Okay, so if that be the case, recall also that force is PA, right? Pressure times area. So from there we can therefore say that work done W is equal to force times distance, so which will be equal to pressure times area times distance. And area times distance is already what? Volume. So work done will be equal to what? PV work done. That's what we call it. PV work done. You would have dealt with it a lot in chemistry. So O-level chemistry. So what are we saying now? Therefore, the pressure energy is going to be the work done per unit volume. So this is what we call pressure energy. Okay? This is the work done per unit volume. So the net work done in moving from point 1, net work done from point 1 to point 2 in our fluid, in our tube, okay, is going to be given by P1 net work done, net W work done is going to be P1 minus P2. Is this clear? Net work is going to be what? P1 minus P2. That's net, right? Subtraction. All right. So that is this side of the equation. Now just follow me. Now the next thing is that, you know, for a moving fluid, it's going to possess kinetic energy. Okay? So since it is going to have kinetic energy, we know that kinetic energy of the fluid, since the guy is moving, it's going to have kinetic energy, right? So kinetic energy KE of the moving fluid is going to be half mv squared. Alright? But the fluid is not moving as one, it's moving in volume, right? So the kinetic energy per volume, which we call the kinetic energy per unit volume here, is going to be equal to 1 over 2 mv squared divided by volume. Okay, so that becomes mv squared over 2v. Keep in mind that this v is different from this v. This small v in physics is velocity, big V is volume. Alright. So and you already know that density, mass over volume is what? Density. So that kinetic energy therefore is equal to, let me write it here. That kinetic energy therefore is equal to mass over volume dot velocity squared over 2. And mass over volume is density. So kinetic energy is going to be rho V squared over 2, or written as half rho V squared. So that's how this portion of the equation is gotten. Alright? Then the last portion is the potential energy. Now the potential energy per unit volume. The potential energy per volume of water. Now, recall that at specific instances in the movement of the fluid, it's going to have potential energy at those points, isn't it? So the potential energy of per volume is going to be P. Recall that P itself is actually mgh, so per volume. Okay, again here we're going to see that we can isolate m over v, so that we have gh here, and m over v again is density, such that potential energy per unit volume is going to be density gh, rho gh. All right. So this is the third part of this guy. Good. Now, what do we do with these two now? You know that the body is moving from point 1 to point 2, so it means that the kinetic energy is also what? Changing. So the gain, there's going to be a gain in kinetic energy because our guy is moving upward here, is moving and the speed is increasing. So if that's the case, there's a gain in kinetic energy, there's a gain in KE, which is measured by taking the kinetic energy at the highest point, second kinetic energy, minus initial kinetic energy per unit volume. So if that be the case, we are going to have gain in kinetic energy to be equal to half rho2 volume velocity 2 squared. Is that clear? This is the kinetic energy at point 2. This will be the initial kinetic energy, that will be minus half rho1 v1 squared. Is that clear? So if this be the case, then we know that the gain in kinetic energy is expressed as, we can simplify it. Now, because it is the same fluid, the density of the fluid is going to be the same. So it's constant for that fluid, so that we can therefore have factorize half, which is common, rho, which is common for the fluid because it's the same fluid, rho v2 squared minus v1 squared. This is going to be the expression for the gain in kinetic energy. How about the gain in potential energy? Remember, the guy is moving upward. Gain in potential energy. The guy is moving upward, so he's going to have a gain in kinetic energy, in potential energy. So what's going to happen here? You therefore know that the gain in potential energy is going to be the new potential energy at a higher potential, which is going to be rho 2 G2H2 minus rho 1 G1 H1. But certain things are also constants here to the fluid. Density is going to be the same. Rho 2 is equal to rho 1. Acceleration to gravity 2 is equal to acceleration to gravity 1. I mean, this does not even make sense because we are on Earth, so acceleration to gravity is going to be the same. So if that be the case, then we know that the gain in kinetic energy is going to be rho G, which is common between H2 and minus H1. So the only difference we have there is in height. So if that is the case, then how did we now arrive at this expression? So let me show you how the expression came to be. Now, given all of these expressions, what is now the net work done? You know that net work done, total energy is going to be the net work done, okay? The actual energy, which is going to be all the energy. So all the energy is mechanical. That is going to be kinetic energy plus potential energy. So we'll say that net work done, therefore, net work done by fluid is going to be gain in the kinetic energy, the gain in the kinetic energy plus the gain in potential energy. So if this is the case, what is the net work done? Net work done is P1 minus P2. So we have P1 minus P2 is equal to, what is the gain in kinetic energy? That is this expression, which is half into bracket rho V2 squared minus, rho into bracket V2 squared minus V1 squared. Okay? Plus, what is the gain in potential energy? That guy, rho G H2 minus H1. Alright. If this is the case, therefore, then we can now express our guy in full such that we have P1 minus P2 is equal to half rho V2 squared minus half rho V1 squared plus rho GH2 minus rho GH1. Alright. Now you'll see that there are expressions that are for 1 and there are expressions that are for 2 here. So we are going to collect like terms, kind of it, like collecting like terms. So these ones that have 1, they'll come together. P1, this one will come here, it becomes plus half rho V1 squared plus rho GH1 is equal to, P2 will come here, becomes positive P2 plus half rho V2 squared plus rho GH2. And this is the expression for the Bernoulli's law. And it states that for a fluid that's an ideal fluid in steady flow, the sum of the pressure energy plus the kinetic energy plus potential energy, all of them per unit volume, is constant. So you see that here is equal to P2 plus half rho V2 squared plus rho GH. That will be it for this video. Do well to subscribe to the channel and click the bell notification. God bless you.